In this video, we're going to talk about inverse trigonometric functions. So the big, thing I want you to think about in this section is when you're working problems, you want to think about what angle has a sine, cosine, tangent, secant, cosecant, or cotangent of some value. So I'm going to write that down. So I want you to think what angle has a sine, cosine, or tangent equal to whatever the thing is in the function. So when you evaluated trig functions, we got a trig ratio as the answer, and we plugged in an angle. Now what we're going to be doing is plugging in a trig ratio, and our answer is going to be some angle. So for any function to have an inverse, it must pass the horizontal line test. So hopefully you learned about that before, but if not, we're going to talk about it a little bit. So I'm abbreviating horizontal line test with HLT. And basically what this test tells you is whether a function is one-to-one. So just as a refresher, the horizontal line test means that you place your pencil horizontally on a graph, and if you move it up and down, if it crosses only one point of the graph at a time, then the function is one-to-one, and that says that it has an inverse. So as an example, let's look at the function f of x is equal to sine of x. So we learned how to graph this function a couple of sections ago. So if you remember, the graph looks something like this. We have our 4 tick marks on the positive x-axis, 4 tick marks on the negative x-axis. We had an amplitude of 1, so this is 1, this is negative 1, and the graph makes a wave shape like this. So we can connect these dots with a smooth curve, and our graph should look something like this. Okay, so the problem with this graph is that if we were to put our pencil horizontally on the graph and move it up and down, you might notice that your pencil is going to cross more than one point. And in fact, it crosses an infinite number of points everywhere you move the pencil. So it fails the horizontal line test. So this is kind of a problem because as it stands right now, the sine function, we can't define an inverse function for it because it fails the horizontal line test. So the big question is, how do we make this function one-to-one? So one thing we can do is we can literally just ignore part of the graph. So what I'm going to do is I'm going to switch colors, and let's say that I just start here and I end here, and I ignore all of this, and I ignore all of this. So if I restrict my domain in this way, this actually leaves us with just this little piece of the graph, which if we then redo the horizontal line test, you might notice that that little piece is now one-to-one. So the way that we make this function one-to-one is we restrict the domain. And what this means is we only consider x values on the interval negative pi over 2 to pi over 2. Okay, so we talked about sine of x. Cosine of x is very similar. So remember that sine of x and cosine of x, you literally just move the graph over a little bit and you can turn one into the other. So we can do the same exact thing with cosine. We can just chop off part of the graph and just say, well, let's look at this little part. Tangent's a little bit different. We'll talk about inverse tangent in a little bit. So first, let's talk about the inverse sine function. So the way that we write this function is we write sine with an exponent of -1 and an x. So when we write this -1 right here, this does not mean 1 over sine of x. Okay, because remember 1 over sine of x is cosecant. So we don't want to do reciprocals. So when we see that -1, that means inverse, not a reciprocal. Okay, another way you could see this written is arc sine of x. So some textbooks might write it a little bit differently, or if you plan on taking more math classes after this, Some of your teachers may write it like this. So the domain of sine inverse is going to be the range of sine. So the range of sine was -1 to 1. So our domain of sine inverse will be -1 to 1. So these are the only numbers we can plug into sine inverse. Now the range is just going to be -π/2 to π/2. Because remember, in the normal sine graph, we restricted the x values, which is the domain of sine. So when we do the inverse, the domain of sine is going to become the range of sine inverse. So this is our domain, this is our range. And sort of a visual way of thinking about this is if we think about our unit circle and we think about the values π/2 and -π/2, basically what we're saying is when you have a sine inverse function, your answers have to come from this side of the unit circle. So we'll make a little note of that. So answers for sine inverse of x must come from this half of the unit circle. And so notice that we have some answers that are negative and some answers that are positive. Okay, so if you get an answer that's in the fourth quadrant, just make sure to rename it to a negative angle. So you need to find an angle that's coterminal to the positive angle you might get that we learned about with the unit circle section, and you might need to change that to a negative angle. So let's do a couple of examples. So first, we have arc sine of -1/2. So what I want to do is on the unit circle, I want to think about where is sine inverse going to have negative values. Well, I know that my answers have to only be from this side, so I must be dealing with an angle in quadrant 4. So the question we want to ask ourselves is what angle in quadrant 4 has a sine of -1/2? So you might think about this little angle right here, which we could say is 11π/6. So if you remember back to the unit circle, the value of the angle that makes sense is 11π/6. However, we know that we need to keep our answer between π/2 and -π/2. So if we wanted to write 11π/6 as a negative angle, we could say that that's -π/6, because we're basically starting at 0 and counting backwards 1π/6. So the arc sine of -1/2 is -π/6. In the next example, we have sine inverse of the square root of 3/2. So once again, if I think about where my answers can come from, this one has to be in the first quadrant because it's positive. So all the positive signs must be in the first quadrant. So now we ask ourselves, which angle has a sine of the square root of 3/2? So if you think back to the unit circle, you might think, oh, π/3. So the sine inverse of root 3/2 is just going to be π/3. So you might be noticing already that it's very important by this point that you know your unit circle. So be very familiar with those values, because now basically what we're doing is going backwards. We're starting with some ratio and our answer is going to be the angle with that trig ratio. So our last example for sine inverse, we have the sine inverse of 2. So there's one little problem with this. So notice that we're plugging in a 2, but our domain for sine inverse was -1 to 1. So this one, we can't plug in 2. It just doesn't work. So what we say for this one is that this value does not exist, and we can abbreviate that as D and E. And our reason is that 2 is not in -1 to 1. So that's just a little bit about sine inverse. Now let's go over cosine inverse in much the same way. So first of all, the way that we write the function is cosine with that exponent of -1 and an x. And then another way you might see this is arc cosine of x. And just like sine inverse, the domain of cosine inverse will be -1 to 1. But the range is going to be a little different. So this time, the range is going to be 0 to pi. So if we think about what this looks like on the unit circle, this means that our answers have to come from that top half of the unit circle. So for cosine inverse, your answers for cosine inverse of x must come from this half of the unit circle. Okay, so much like we did with sine inverse, we're going to work a few examples just with cosine inverse. So the first one, we have arc cosine of the square root of 2 over 2. So the question we want to ask ourselves is which angle in quadrant 1 or quadrant 2, so maybe I'll draw the little coordinate grid there. So on this half of the unit circle, which angle has a cosine of positive root 2 over 2? So since the ratio is positive, we know it must come from the first quadrant. So it's going to be some angle in here. And if we think back to our unit circle, the angle on the unit circle in the first quadrant with a cosine of root 2 over 2 is pi over 4. So our answer to arc cosine of root 2 over 2 is pi over 4. For our next cosine example, let's consider the cosine inverse of -1. So once again, let's think about our little picture. So this time, since we're plugging in a negative number, we know the angle must come from quadrant 2. So if we think about our unit circle and we think about, well, what angle in that second quadrant has a cosine of -1, the answer is pi. So the cosine inverse of -1 is pi. And then finally, we have the cosine inverse of 2. So this one turns out exactly like the sine inverse of 2. The problem is 2 is not in that interval from -1 to 1, so we can't plug it in to begin with. So for this one, we don't have an answer, so the answer does not exist. And the reason is that 2 is not in -1 to 1. Okay, so that's a little bit about cosine inverse. Now we're going to talk about inverse tangent. So this one's a little bit different. So the way that we write the function is we say f of x is equal to tan inverse of x. So we, again, use that little exponent of -1. And another way you might see this written is arc tan of x. Okay, so inverse tangent is a little bit nicer than the other two because we don't have to worry about what numbers we're plugging in. So inverse tangent, we can actually plug in anything we want. But our answers have to come between -pi over 2 and pi over 2. So it's similar to arc sine or sine inverse. However, our picture is going to have little open circles at the top and bottom because we're not including those values in our interval. And the reason for that is if you think back to the unit circle, values of tangent at those angles do not exist. So since the tangent values at those angles do not exist, well, we can't get them as answers. Okay, so once again, answers for tan inverse of x must come from this half of the unit circle. Okay, so let's try a couple of, well, actually, before we do the examples, I just want to show you what the graph of tangent inverse looks like. So if your plan is to take calculus after you're done with this class, then I would say that tangent inverse is probably the most important of these three functions that you know what it looks like. So we're going to just talk about the graph really quick. So the graph of tangent inverse of x. So we're going to draw our x and y axes. And so the way that tangent inverse looks is we've got a horizontal asymptote up here at pi over 2. And we've got another horizontal asymptote down here at -pi over 2. And then in the middle of this, we've got a sideways looking tangent. Okay, so I think this graph is the nicest one to show you because it looks the most like its original function. So this really gives you that idea of what it means for two functions to be inverses. So basically what we've done here is just taken the tangent graph and we've reflected it in a certain way that it turns sideways like this. So if you think back to the original tangent graph, we had vertical asymptotes at pi over 2 and negative pi over 2. So since this is the inverse, we're just swapping all the x's and y's around. So our vertical asymptotes become horizontal asymptotes, and then our graph turns sideways like this. Okay, so that is the graph of tangent inverse. And now let's go through some examples of how to evaluate inverse tangent. So this one can be a little tricky because you're kind of thinking about the sine and the cosine at the same time. So our first one, we have arctan of 0. So what we're asking ourselves here is which angle in the first or fourth quadrant has a tangent equal to 0. Okay, so since the tangent is, well, 0 is not really positive or negative. So right there, we know that it must lie right in the middle of the first and fourth quadrant. And the angle that does that is 0 itself. So the arctan of 0 is 0. Another way to think about this is you could think about what the sine is, because we know that tangent is equal to sine over cosine. So we could also consider, okay, if tangent 0, then I know that this fraction of sine over cosine must also be 0. The only way to do that is if sine is 0 and the angle where sine is 0 is 0. So if that confuses you, it's okay. We're going to do it again with this tangent inverse of 1. But that's kind of the idea. So if we look at this tangent inverse of 1 example, I think this one's easiest to think about if we really consider that identity tangent of theta, be a little more careful this time when I write it out, is equal to sine of theta over cosine of theta. So our question is, which angle has a tangent equal to 1? So first of all, since the tangent's positive, it must be in quadrant 1. Okay, and also since tangent is 1, this means that sine over cosine must be equal to 1. So the way that we have a fraction equal to 1 is if the thing on the top of the fraction and the thing on the bottom of the fraction are the same thing. So our question becomes, which angle in quadrant 1 has the same value for sine as cosine? And if you really think about your unit circle, there's only one angle that's like that, and it's pi over 4. So remember that pi over 4 has sine equal to root 2 over 2 and cosine equal to root 2 over 2. So if we divided those to get tangent, we get that value of 1. So again, tangent can be a little tricky, so if you have trouble with that one, please let me know. Okay, for our third example, we have tangent inverse of negative 8.45. So this one's different than the ones that we've talked about before because this one is not on the unit circle. So if you see a decimal like this signals to you that you will need to use a calculator. And you're going to need to figure out which mode to put your calculator in based on what you want your answer to look like. So we're going to do it both ways just so that you can check. So if we were to plug this into a calculator, and your tangent inverse button, if you've never had to use it before, should be like above your tangent button. So you might have to hit like second function and then tangent, and that should give you the tangent inverse function. But anyway, if you were to type this into your calculator, if you're in radian mode, you should get negative 1.453 radians. And if you're in degrees, you should get negative 83.25 degrees. So it's very important when you're reading a problem in 6.3, or anytime you're using inverse trig functions, make sure you're clear on which unit you want your angle in. So if the directions say degrees, make sure your calculator's in degree mode. If the directions say radians, make sure your calculator's in radian mode. So we're going to try one more just so you can get some practice punching stuff into your calculator. So this last one, we have the sine inverse of 0.2447. So just like tangent inverse is usually the tangent button, but like a second function, the sine inverse is usually right above the sine button. And if we were to type this in and we were in radian mode, we should get 0.247 radians. Or if you're in degree mode, you should get 14.16 degrees. So it's very important, once again, that you pay attention to which mode your calculator is in, because if you use the wrong mode, your answer will not be correct. It'll be in the wrong units. Okay, so that's just a little bit on how to use the calculator. So now we're going to take everything that we've learned about sine inverse, cosine inverse, and tangent inverse, and we're going to apply it to some problems. So for this first one, we're going to find this missing angle in degrees rounded to 1 decimal. So the first thing I'm going to notice is, since this problem says find the angle in degrees, this tells me my calculator better be in degree mode. All right, so make sure your calculator's in degree mode, and then let's figure out how to relate everything in this triangle. So the first thing you might notice is that the two sides we're given, we can label as either the opposite, the hypotenuse, or the adjacent side. So let's do that. So we have 30 is across from this angle theta, so it's going to be the opposite side, and 70 is the hypotenuse. So the two sides we're given are the opposite and the hypotenuse, and our next question is, well, how do we relate those two sides? Which trig function contains the opposite side and the hypotenuse? And so you might be thinking sine. So what we're going to do is take the sine of theta to be equal to 30 over 70. Okay? And so now what we want to do is we want to solve this equation for theta. So this might be a little different than the way you solve equations before. So this theta is not multiplied by sine. That's very important to point out. So we can't just divide by sine over here and have theta by itself. Okay, this is where our inverse functions come in. So instead of dividing by sine, what we do is we take the sine inverse of both sides. And what this does is the sine inverse cancels with the sine, and we're left with theta equal to the sine inverse of 30 over 70. Okay, so once again, very important to note, we're not dividing by sine, but this sort of does the same thing, if that makes sense. So to move sine away from theta, we need to take the sine inverse. Okay, and finally, if we put this into our calculator in degree mode, we should get 25.4 degrees. So that is our answer. So for this next example, we're going to find all angles between 0 and 180 degrees satisfying the given equation. So this time we're going to solve similar equations to the one we just did, but we're not given a triangle. And we want to round to 1 decimal place. So for this first one, we have cosine of theta is equal to 3 over 4. So the first thing I'm going to do is solve for theta. So the way that we do that is we take the cosine inverse of both sides, and this leaves me with theta equal to cosine inverse of 3 over 4. So next, I need to put this in the calculator, and if I do that in degree mode, because we said between 0 and 180 degrees, we get 41.4 degrees. Okay, so the last thing I need to do is I just need to check that this is the only angle that's going to do that. So if I draw my coordinate grid, and I think about 0 and 180 degrees, well, that's 0 and this is 180. I want to think about, is there another angle that can possibly have a cosine of positive 3 over 4? And the answer is no. So a positive cosine must come from this first quadrant. Okay? And so for each angle in this first quadrant has a unique cosine. So like no two angles have the same cosine in this first quadrant. So that tells me that this 41.4 is my only answer. So you might be like, well, how could I get two answers? Like, is that even possible? Well, we're going to see in the next example why we needed to check and just make sure that that's the only answer we could get. So in this next example, we're going to solve tangent of theta equal to negative 20. So again, the first thing I'm going to do is take the tangent inverse of both sides, and so I get theta equal to tangent inverse of negative 20. And if I put this into the calculator, I should get your calculator should give you negative 87.1 degrees. Okay, now this is where we want to pay attention to what this angle is telling us. So let's draw a picture. So negative 87.1 degrees is going to be somewhere down here. But there's a problem with this answer that the calculator gave me. And the problem is that if we go and look back at our directions, we notice that we want an angle between 0 and 180 degrees. So 0 degrees is over here, and 180 degrees is over here. So negative 87.1 is not in quadrant 1 or quadrant 2. So that's a problem. So this is not actually our answer. So what we want to do is find not an equivalent angle, but we want to find an angle that basically gives the same information about tangent, but is in quadrant 1 or quadrant 2. Okay, so we need an angle with a negative tangent. So it's going to be somewhere in quadrant 2, because quadrant 1 we only have positive values for tangent. So our angle must be in quadrant 2, and in fact, it's going to be directly across from this angle that we got in quadrant 4. And the reason for this is that, well, to get that same ratio, your x and y values have to be the same, just with opposite signs, basically. So what's going to happen is we want the angle directly across from this negative 87.1. And so what we can say is that if this angle is 87.1, well then this angle must be 87.1 as well. And so our question is, well, what's this angle in here? So we want that angle between 0 and our line. So the red angle is what we want to find. That's our big question. So how do we do that? Well, we can think about 180 degrees. Well, we know 180 degrees is the straight line here. And if we take away that angle of 87.1, we should be left with the red angle. So what we're going to do is do 180 degrees minus 87.1 degrees, and this should give me 92.9 degrees. So our answer is 92.9 because it's between 0 and 180 degrees. So if we had not had that constraint in the directions, that negative angle that we initially got would have been fine. But since we had that constraint of between 0 and 180 in the directions, we had to be very careful about where our angle actually was. Okay, so hopefully that makes sense, but again, if that's confusing, please let me know. So what we're going to do now is we're going to combine a few of these functions. So we're going to ask ourselves, what happens if we maybe take the inverse trig function of some value, but then turn right back around and take another trig function of that answer? So these are like composite functions. So you might remember like f of g, g of f from a previous class. That's basically what we're doing here, but just with trig functions. Okay, so let's look at our first example. So we have tangent of cosine inverse of 2/3. So what we're saying here is that this cosine inverse of 2/3 is the number that's plugged into tangent. Okay, so it's not multiplied or anything like that. It's a function inside of a function. So the way that I usually think about these is I think of this as my inside and this is the outside. So there's a reason why I'm labeling this, because we're going to talk about like what's a good strategy for these. So the first thing you want to do for these is we want to solve that inside function. So what we're going to do is we're going to solve a triangle for the inside function. And what I mean by this is we need to, so we know that any trig function defines a triangle. So I'm going to go ahead and draw a triangle, and I know that this triangle should be in quadrant 1 because my cosine value is positive. Okay, so my triangle is going to look like this in quadrant 1, and I know that my cosine is equal to 2/3 because cosine inverse of 2/3 is my inside function. So I'm going to write that real quick. So cosine inverse of 2/3 means that cosine of theta is equal to 2/3. So if this is my angle theta, then I can label the sides of my triangle like this because 2 is the adjacent side and 3 is the hypotenuse. So all I need to do to solve this triangle We don't need to worry about the other angle, but we do need to get that missing side. So the way I can do that is with Pythagorean theorem. So I'm going to take the square root of 3 squared minus 2 squared, and that's going to be the square root of 9 minus 4, which is the square root of 5. So this missing side has length square root of 5. And so now that I have all three sides, I can get any trig function of theta that I want. Okay, so my second step is going to be find the value of the outside function using the triangle. So in this case, our outside function is tangent of theta. And so if we look at our triangle, we get tangent by taking the opposite side divided by the adjacent side. So we're going to have the square root of 5 divided by 2, and this is actually my final answer. So what I did was I took the cosine inverse on the inside, and I turned that into a triangle drawing. Okay, and once I had all three sides of that triangle, then I could find tangent of the angle without actually knowing the angle. So that's probably important to point out. So in these problems, we're not finding theta, okay? We're using the information about one of the trig functions of theta to get another trig function of theta. All right. So we're going to try another example because sometimes these are very confusing. Okay, so this one we have the cosine of sine inverse of negative 3 over 5. So once again, the first thing I'm going to do is look at this sine inverse of negative 3 over 5, and I'm going to draw a triangle. So this one's a little trickier because our sine has a negative value. So remember that this means that sine of theta is equal to negative 3 over 5. So I know that sine inverse can only have answers in quadrants 1 or 4, and since the sine is negative, then it must be in quadrant 4. So this time my triangle is going to look like this, and this is going to be my angle theta. So the way I'm going to label these sides is I know that my hypotenuse is that bottom number of 5, and I know that the opposite side must be 3. Now my question is, what side does that negative go on? And the answer is, well, a hypotenuse is never going to have a negative value. So you're always going to assume that the hypotenuse is positive, and you're going to put the negative with the other one. So in this one, it kind of makes sense because you see how this vertical side is in the negative y values. So it kind of makes sense that we would then label this side with a negative 3. Okay, so let's find that missing side up here. So the way we're going to do that is, once again, we're going to use Pythagorean theorem, and we're going to say 5 squared minus negative 3 squared is equal to 25 minus 9, which is the square root of 16, which is 4. So this top side of my triangle is just going to be 4. So now that I've found all three sides, I can compute the cosine. So now I want to think about, well, what's cosine of theta? And if I look at my triangle, cosine means I need to take the adjacent side and divide it by the hypotenuse. So cosine of theta is equal to 4 over 5, and that's going to be my final answer. Okay, we're going to try one more just so you can get used to this process. So this third example, we have cosecant of cosine inverse of 7 over 25. So once again, first thing I'm going to do is draw my triangle. So cosine inverse, remember we can be in quadrant 1 or quadrant 2. Since cosine inverse has a positive number inside of it, we must be in quadrant 1 because that means that cosine of theta is equal to positive 7 over 25. So our triangle looks like this again. This is theta, and then my adjacent side is 7. My hypotenuse is 25. Our next step, we use Pythagorean theorem to find that missing side. So we have 25 squared minus 7 squared is equal to the square root of 625 minus 49, which is the square root of 576. which is 24. So my missing side is 24. So now that I've solved this whole triangle, or I've got all three sides anyway, now I can think about, well, what's the cosecant of theta? And so remember that to find cosecant is basically 1 over sine of theta. So if we know how to find sine of theta, we basically just have to flip the fraction, and that gives us cosecant. So sine of theta from this triangle is going to be 24 divided by 25. So if we flip that around, we get 25 over 24 for the value of cosecant, and so that's my final answer. 25 over 24. Okay, so the last thing we're going to talk about with inverse trig functions is we're going to talk about a quick little word problem. So our word problem goes like this. Special Agent Michael Scarn wants to parkour on top of the dumpster at the Scranton Business Park. He plans to jump from a distance of 4 feet away from the dumpster. So our first question is to express the height of the dumpster as a function of the angle of elevation. So let's draw a little picture and see what this looks like. So let's assume that this vertical line's the dumpster, and this is the ground, and he's jumping from here to here. So this is our triangle, and we know that the jump will be 4 feet away from the dumpster, so this side is 4. We want to find the angle of elevation. So remember that that's the angle between the ground and that line of sight. So that's going to be theta, and then I'm just going to call the height of the dumpster h. Okay, so now I've got the height, the angle, and that other side of 4. So I can actually relate all of this now with a trig function. So 4 is the adjacent side, and the height is the opposite side. So I can use tangent and relate these two values. I can say tangent of theta is equal to h over 4. So now let's look again at our question. So we want to express the height of the dumpster as a function of the angle of elevation. So anytime you see a question that says express something as a function of something else, so think of the height as the y value, and think of the angle of elevation as the x value. So what we want here is we want to get h to have a formula with only theta in it. So we want to get h by itself, and everything on the other side of the equation needs to only have theta in it. Okay, so let's see how to do this. So if we want to get h by itself, maybe the first thing we want to do is multiply by 4. So we have h is equal to 4 times tangent of theta, and right there I have h by itself, so I'm good. So one last way to write this is we write h of theta is equal to 4 times tangent of theta. So I just want to point out that the reason we do this is we're describing what the variable in the function is. So as a little note, when we write h of theta, this does not mean multiplication. So this doesn't mean multiplication. So it just tells you what variable you plug in. So sometimes when you read these problems of like express something as a function of something else, sometimes it gets a little confusing as to what you're plugging in versus what you're getting out. And so a way to keep that, I guess, less confusing is using this function notation right here. So that's telling you that you've expressed h as a function of theta. Okay. So let's do another problem related to this. So now we want to express the angle of elevation as a function of the height. So this time the angle of elevation is y and the height is x. So what this means is we're going to start with that equation that we got, tangent of theta is equal to h over 4, and this time I want to get theta by itself, and I want to have h as my only variable on the other side. So how can we get theta by itself? Well, as it stands here, it's trapped inside of tangent. But what I can do is take the tangent inverse of both sides to get theta is equal to tangent inverse of h over 4. Okay, so this is good. I've got theta by itself, and h is the only variable on the other side. So my last step is just to write this with function notation. So this time we're going to have theta of h is equal to tangent inverse of h over 4. So once again, this is not talking about multiplying, it's just saying that the only variable on the right side is h. Okay, so the last thing we want to do is actually take these two formulas we found and apply it to actually finding an answer for something. So what we're going to do is we're going to find the angle of elevation if the dumpster is 6 feet tall. So since I want to find the angle of elevation, I'm going to go with the formula that I found in part B. So I'm going to have my angle of elevation as a function of h is equal to tangent inverse of h over 4. So let's think about why I chose this one. So I'm being told that the dumpster is 6 feet tall. So I'm being given an h value that I can plug in, and I want my answer to be an angle of elevation. So that's why I chose the formula with h as the plug-in variable and theta as what you get out. So let's actually evaluate this. So we're going to have theta of 6 is equal to tangent inverse of 6 over 4. So 6 over 4 is 3 over 2, but that's still not a nice value that we get from the unit circle. So I'm going to need to plug this into a calculator, and let's assume that we want the angle in degrees. So if I plug this into a calculator in degree mode, then I should get roughly 56.3 degrees. So that angle in our picture at the top is roughly 56 degrees. All right, and this concludes our 6.3 lesson.